Is everybody be able to see my screen?
Yes.
Okay, cool. Yeah, today I will basically cover over maybe last a few years. There are some applications I've developed for, especially on spectroscopy. So yeah, I will have a little bit, maybe maybe 1 or 2 slides that I applied on IOBeam 3 thing, specifically for this group's interest. Yeah, but most will be more generic material science applications. And yeah, it just this has been like a long, maybe over a decade development across multiple programs. Yeah, yeah, I have got my colleagues previously from Oak Ridge too, which yeah, I will share at the end. You can use some of the code in GitHub as well. Yeah, the motivation here is really over the last maybe since the first CCD comes, we have a tremendous amount of yeah, I'll use a laser point of data. So we are gradually, increase from 4 GB per hour. Nowadays, because of the 40 stem, we are almost acquiring 100 terabyte per hour data scale. So it's almost impossible for like a human to just analyze such a oversampling amount of data. So what we are trying to do here is we're trying to resolve this issue so that we can be able to analyze the data at a relatively efficient manner, but also we'll be able to improve the visibility. So I will show 3 different perspectives through our method. So on the right is kind of a cover page published during COVID using this method. So we'll be able to showing a few cases on chemical segregation using unsupervised machine learning, and also coupled with recently getting more and more popular with a montage large scale SEM or STEM mapping. Yeah, so there's a just QR code, but yeah, it's yeah, I have some sample codes from Cambridge and yeah, some of the earlier year development in this area, but let's go and check maybe with the most difficult case. So this is one of the hybrid field. So a lot of you guys, if you don't have the background in irradiated materials, so basically you have all these transmutations of different fission products. So then you will forming a lot of the fission gas bubbles and a lot of these multi-component precipitates usually consists of like moly, all these transition metal materials. So what we are trying to looking at is at the periphery of these field palettes. So you're seeing these kind of segmented regions. So these are not because of artifacts, but they are actually happening because in the periphery, because of these diffusion gas bubbles, we are reconstructing the grain boundaries near the periphery of these field palettes. So what we are trying to looking at is, first we want to make sure these xenon krypton bubbles or any of these migrated bubbles are being kind of located in this not relocated in the restructuring region, but we want to try to see the radial distribution of these fission products, so then we can increase the burn up for these fields. So in a traditional manner, if you trying to do a full length scale characterization, it's very lengthy, so you have to spot at different regions. For example, on this, figure B here, you are seeing these kind of, over under focusing, be able to review these xenon bubbles, but sometimes, the xenon bubbles are varying from different length scales. So these are nano size, but, some of these here, even, in an SEM scale. So it's kind of a mass kind of, combine of different types of voids and cavities and all things like that. So you will be able to distinguish at different length scales. So traditionally, when you do the select area diffraction patterns, you will be able to, see this, for example, on this top right, there are two precipitates. So you will be able to, see the structure from this area electron diffraction. But this is, causing a lot of time to interpret the data for just, one set of image for like a teeny tiny area. So for more generic microstructure, you need a more holistic stand view to represent such type of analysis. So what we are trying to do here is if we looking at the X-ray map. So what I mean by that is if we are taking the XY pixel in each of the plane, so behind, either it's a EDS map or EOS map, you will be able to get a distribution. Yeah, this is borrowed from Gatan. So regardless, for this, we are not trying to, identify any or do quantitative analysis like, previous seminars we talked about, using supervised machine learning to do quantitative analysis. So this one, we're just trying to focusing on reduce the background noise and try to review more principal component analysis method. So there are different steps. So first we are trying to making this matrix here. We put into a Poisson space. So then we can do the scaling to make it a more almost static matrix. And then we can apply different types of filtering methods that we call it, either as a single value decomposition or PCA method. But then we need to find the solution of that matrix D. So what you're gonna do is we call this factor PCA method. But however, sometimes you will hit the singularity. So then you have to do the matrix rotation. Yeah, this is just a general step. So in reality of our coding is we are, this is a thermoofficial Talos microscope. So you can obtain on the original data from all these different types of transition metal precipitates, and then you can either do a live processing or you can download it either using the Bruker. There's a I forgot the name. Yeah, either the Bruker or VROX. Yeah, whatever software you have, or whichever vendor. So you can transfer the files which is compatible to HDF5 files. So then you can do the labeling, store in the Amazon cloud or whatever you want to label. Yeah, and when this couple with a map software or like the montage with Aztec, you'll be able to do the automatic mapping of a relatively large area. I will show in the next few slides. So for example here, we are trying to investigate a relatively small region of a kind of 5-year service field palettes. So what you can see here are all of these different contrasts. There are overlapping of precipitates, but also they are overlapped with the xenon bubbles. So how can you distinguish different components from these X-ray signals? So one way to do this is you try to rank all these different types of signals through the PCA score. So there we call like a different abundance and named by the number. So what you're seeing here is, for example, abundance 1 is, predominantly by all these, 6 types of elements, and abundance 2 are more, pronounced with the xenon signal. So in that way, we can, relabel all these maps, and we are showing like these type of nanometer scale xenon bubbles in this image, and then you can reintegrate the map, precisely showing the locations, and you can also do the density and side distribution of these xenon bubbles. The next is how we can, the first is we distinguish the different components, and the second is how we can review things that sometimes, conventional microscope cannot, easily resolve. So this is an image of a grain boundary. So if you really, try to, I mean, I don't know if you guys were able to see any contrast. Maybe, it's either video or resolution. Can anybody see anything at the grain boundary, or you just see maybe?
Yeah, there is some difference between the images. Yeah, we can see the line.
But it's hard, right? So if you printed this on like A4 or letter size paper, almost impossible to see these contrasts. So what we're trying to do here is, if we just take the STEM EDS map at the same area, and then we can do a relatively, higher, looking at not just the L peak, but looking at other M peaks as well. So you'll be able to see like the smaller ones are actually the xenon bubble, and the bigger ones at the grain boundary are these moly enriched precipitates. So this way, you can be very confident that what you are anticipating is from the data is actually precise. Especially, you're looking at these intergrain boundary. There are a lot of things in niobium sorting as well. You can easily just apply this method as well. So, and then for this specific hybrid enough system, a lot of people, back in the 60s, they created all these different types of, phase diagram. So what we're doing is we are just, looking at maybe over, let's say 5,000 precipitates. This is only 1/10 of the data, but you'll be able to, plot a map of all different types of composition of each and every precipitate. And then you can, kind of getting a trend of the system, then, reinterpret the, this phase diagram here with some classic thermodynamic model. This is that's on video, but I'm not gonna play here. And then if we are just, try to apply this method, this is one of the kind of a thin film fabricated by Ultramat on a copper substrate. So if you're trying to looking at one of the grain boundary, this is just a random high angle grain boundaries in the niobium 3 thin film. So if you doing a relatively, this is a 2 micron scale bar. This is just a high resolution image. So what I'm trying to do is I want to see if there is anything peculiar at the grain boundary. So in this raw EDS map data, because we are having a relatively low counting EDS detector, also depending on the sample tilting and angle, all these things can affect your data. So however, if I'm, try to, if you just see the copper signal, it is very low. But if we just using our method, we will able to see, there's like a small precipitates near the grain boundary, and also we're seeing a little bit of the copper segregation at this grain boundary. which is very beneficial because the original data queue is not showing that. Yeah, and then we can apply this to other systems. Yeah, this is just like a generic approach. So there are some irradiation induced segregation in some silicon carbide. Yeah, this is also interested material for fusion applications. Yeah, so yeah, they're also interested in such kind of applications. And this is some like alloy system. It's an iron, chrome, aluminum system. So what they are looking at are on the right side. Yeah, there are a bunch of dislocation loops and alpha prime precipitates. Yeah, these are by atom probe. So, but what I'm trying to point out is some people really like 3D material science, but if you just want to quickly looking at your microstructure, for example, here, there's a denuded grain boundaries which is kind of deficient in the chrome. So you will find this kind of very regions in this is a atom probe tip. Basically the same, but if you just compare the time span on each of the analysis, so yeah, this atom probe will take at least 4 hours for collecting one tip and doing some of the reconstruction of the isosurface. Yeah, it will require a lot of specific knowledge domain but like for the STEM EDS, you are not just getting a way larger area, but also you can apply the code relatively faster and give you more generic, not generic, but larger EDS area compared with just a localized tip, which is very good for most people. They are, especially for the thin film, and also for Replico also, they are very interested in a larger area rather than some like the nanoscale level variations. Yeah, this can also apply to some of the amorphization during irradiation. Yeah, some of the things are very interesting because all the fusion programs nowadays are very interested in looking at the irradiation effects on superconductors. So yeah, so this area is definitely involving. Yeah, then I mean I'm not gonna say all these stuff because these are not these are more specific to that specific alloy system. But after you getting everything, for example, here you can compare with the MD simulation to see if there's like irradiation induced channeling. With that type of method, you will be able to give quantitative comparison. Yeah, and also this can also be used for high resolution TEM and yields. Yeah, you can do simple like image filtering method using the PCA to filter some doing the energy filter TM, seeing some of the speckles. That's some of the fellows also in Berkeley, they do that in short range order for high entropy alloy system. So also you can see if there's some hydrogen peaks in this is material from spallation neutron stars in Oak Ridge. So what they are seeing are some of these smaller we call it a disordering phase. Yeah, so there you see this green is the helium concentration. There are also some of the hydrogen peaks once you using just all different types of NF NF MF or other method to filtering the spectrum image, be able to show because the challenge here is the hydrogen and helium are near the plasma peak. So what you are trying to target is you really want to showing a high resolution details in such type of analysis. So using just filtering the background, you'll be able to review these features Yes, and then these are some of the early days on some nanoparticles. Yeah, you can try that for some simple component system. This is just for like a bimetallic nanoparticles. Yeah, you can just use their code to start to getting familiar with such type of EDS analysis. Yeah, and then the last part I want to cover is a trending with all these microscopy companies, right? So they develop these products that able to helping us do the montage and automatic image. So for example, yeah, these are like 3 layers. So what you are usually doing is you are gonna store all these XY positions, and then you are going to store whatever spectrum data you want to acquire. So for example, on this let me give this is just a general cartoon. So you, for example, you want to have a 2x2 2x2 tiles in collecting a relatively large area. So but you also want to keep the resolution to be able to see those nanoscale or maybe certain spatial resolution features. And then after you getting all these data from the software, you'll be able to stitch them together, but also depending on your stage, right? And so some noise or like background or maybe sample is drifting, or is those kind of things can really affect your data acquisition. But regardless, after you get this final image on the top left here, you can really be able to stitch like these four. The idea is if you just get a low mag image, you won't be able to resolve all these nanoscale details. Yeah, I'm just gonna using some of I've been working with Dima on some of the replica tapes. So this is just sort of a montage. It's not ideal. You see sometimes you're getting these lines. Yeah, but yeah, these are one of the challenging stuff. Yeah, these are after like stitching the maps. Yeah, but you'll be able to seeing all these tapes. Yeah. This is actually the delaminated tape, so they're trying to do some mechanical testing. Yeah, the details, it's they're gonna publish this soon, but this is a kind of a generic idea, but depending on the data cube, you can easily extract these maps with greater confidence. I'm gonna show you this is a very interesting demonstration here. So what I'm trying to show you are 2 different systems, again using this large scale tile mapping. So this is 10 by 10 100 maps, about 2 terabyte of data, and the second one is 3D printed aluminum alloy. So let's see how this math is gonna give us. Yeah, so this is just like using my master from one single tile data. You're be able to seeing these, especially the moly and these vanadium precipitates, which are these people very interested for fusion applications. But yeah, the beautiful part is you can do all these either the spatial, or you can do the organized PCA method to getting the distribution of the precipitates. This is a very, I think, this is almost this is 5 by 5 micron size, so relatively large area, almost at a SEM scale. But after reconstruction, you easily seeing, especially if vanadium precipitates. Yeah, then the second one, after we extract the data, we can be able to reconstruct each single tile and then stitch them back together. So you are seeing here are some of the cerium precipitates in the aluminum alloy. So yeah, this method is kind of very useful, especially when you are zooming in and then stitch them together, and using the machine learning method to extract all these nanoscale features. Yeah, these are just some of the things from the eigenvalue plot, so you'll be able to see different spectra numbers for the ranking. So this last one is actually very helpful. But yeah, so some of as I'm mentioning, yeah, there are still like on the development part. For example, this image 2 here, there are some of the missing tile during the acquisition, because yeah, as I said, sample might drift or during the acquisition, or yeah, there are some other weird aspects might happen. So you will be able to tune your instrument at an ideal condition. Yeah, this can be done either in TM or SEM. So I think Raman or some other spectroscopy, you can also use this method too. But what I'm trying to point out, you can overlapping, for example, like image 0 and 1. Yeah, you'll be able to see the different locations with the vanadium is relatively larger precipitates compared with other chrome precipitates. Yeah. Again, after reconstructing the map, yeah, I'm just showing you this rectangle area here. Yeah, the copper cerium precipitates are showing in this last image. Yeah, so but sometimes you're still getting low signals from certain points, but yeah, you'll be able to see this after you apply the processing code. So but the original data, it's very vague, so you won't be able to see such features. But even that, as I said, you have to be careful to set up your auto mapping parameters. Yeah, and yeah, these are some of the resources you can download. You can yeah, actually Colin offers, yeah, he did a tremendous amount of work in 4D STEM. So some of the codes are actually transferable. So yeah, the ideal case for these days is people trying to step a augmented analysis for whatever structure property relationship. For example, superconductors, they really want to increase the JC and IC with alternated processing through the microstructure characterization. Through this method, we will be able to iteratively improve our characterization cycle by at least 1 magnitude of order. And also the recent trends of deep learning and auto mapping softwares can greatly improve the efficiency of the characterization cycle, which giving us very good confidence and accuracy of the spectroscopy data we have obtained. Yeah, yeah, if you want to ask questions, yeah, I think I kind of covered a varieties of systems by applying this method. Yeah.
Thank you so much. And now, yes, the floor is open to questions. Don't see any hands just yet, so I'll start. Very general question first. So it seems like, yeah, your slides have a lot of very useful references. Do you think you could share them afterwards?
Yeah.
Perfect.
Yeah.
So also is that, if I understand sort of the general workflow, at least for say, taking an example, the Repco example that you mentioned. So you use like the imaging detector, either like secondary electron or backscattered, to actually take the tiles and then stitch them, and
Yes.
using that data to actually stitch the EDS maps as well.
Yes. Yeah.
Okay. Sorry, perhaps I missed some of the details regarding the PCA analysis. So how does actually the mechanics work of it, and or is it? I think you mentioned some references in papers that will be useful references to go over. But could you go over once more, like the actual the workflow that for the principal component analysis, and that the major sort of the outcome of this is to sort of reduce the noise floor? Is that right?
Yes. Yeah, the goal is you are comparing the spectrum data. For example, you can bing the data, and then you can compare, like let's say if we don't bing, we just do the one by one, and then you can compare each of the spectrum from that pixel, like, and then you compare with the surrounding matrix pixel, and then you can do these type of matrix operations to filtering the noise. Yeah, and then you can rank all different signals from the spectrum. For example, there are like 10, so the first 3 or 4 are the major dimensions. Yeah, then you can just pick those signals from the pixels and reconstruct your map. Yeah, so actually, like, you can using this as a let's say, like, if you can actually use this as a pre-selected or preliminary, or like a pre-filtered data to feed your deep learning software, like Carl, like he showed us previously, right, with the Bruker. Yeah, you can use this more identified or more categorized data to feed the machine learning neural networks to let it train, which will reduce the time. Actually, yeah, we have done this for some of the nano precipitates. Yeah.
Right. So it's just one sort of a good pre-processing step for further analysis and further labeling.
Yeah, you can get a much cleaner data ahead before you actually train the algorithm. Yeah.
Got it. So are you currently working for applying some of these techniques to superconductors? I think you showed some examples regarding the Repco.
So
is there any
one
others?
thing is I work with Peter is we try to figure out some of the segregations in the niobium sweeting. And the other is Dima is trying to see the whole cross section of the Repco tape.
So in the slide, actually, I had a question. So in the EDS map, I think it was that's just a slide that you had just before on the screen already. Slide 12, 11. Could you go a little bit deeper in terms of the sort of the lower panel? So in the EDS data raw, the two sides is that like niobium 310 and niobium on one side and the other?
Oh
Just to get
no,
some background.
no. This is just the one grain boundary in the niobium 3-tin film. I'm just picking a random grain boundary. Yeah.
Right. So this is the STM data or TM data. Is that right?
It's STEM. Yeah, STM.
Yeah.
Yeah.
All right. So 2 grains, and you have actually can show the
copper. Yeah.
segregation.
Copper segregation at the grain boundary.
Right. That comes from the complementary EDS data, right? Okay.
Yes.
Or okay.
Yes. Like after you process the data. Yeah.
Right. Very nice.
Yeah. I mean, but this can, because our EDS is not how do you say, like the recent day, like 4 detector EDS, like it's, the efficiency is a little bit, not a little bit, actually, like maybe only a quarter of these days high efficiency detectors, but yeah, we'll still be able to review these features. So some of the institutions, they might be interested in using this, rather than waiting for a very long time to get a lot of data.
All right. Well, if it is is still waiting for questions, so you can, actually, if you can then talk a little bit more about the RepCode example as well. That was quite interesting data set you had. If you could share
So
some
the
of
rep, so this one I haven't applied our code yet, because it's I have some problems to export the Oxford. Yes, it's unlike the Bruker, actually. I'm not trying to like give some compliment, but yes, the Oxford Aztec is kind of a weird, like they have a RPL. It's a data format issue. So these have to, basically, I have a smaller hard drive, so these 3 data are like 5 terabyte after like we export it. But so one of the interesting thing here is so people trying to see which layer of the replica is actually delaminated. So using this method at a like a relatively large, let's say this is 1 millimeter by 1 millimeter, or something equivalent to that length scale, you'll be able to see like at which location of the 12 millimeter tape is actually delaminating. So that gives you a better perspective, especially you're gonna see the failure at which location of the replica tape. This can I mean, even without the machine learning, you'd be able to have an idea at least.
Right. Yeah. How long did one of these sort of mosaics take?
Each one so this 8x11 is like 8 or 8.5 hours. Probably. But you just let it run overnight, then the next day you'll be able to see it. Actually, this Fujikura tape is having less problems. Because as I said, I have to tune the focusing and contrast to make the auto mapping work.
Okay.
These are just some of the initial. We have been working on this, trying to find a better way to show these type of features.
Right. So that's a good question in terms of if there's a drift or like the source, electron source, like the intensity changes over time, the stability of it. Does it affect the outcome or the analysis? Do you have any issues with that, or?
Yes, I will definitely. That's what I'm saying. You need ideally you want to have a flatter surface. I mean, these tapes, you don't need to polish them, but I don't have any issues with the niobium or niobium 3 tin samples, but yeah, some of these tapes are a little bit hectic. So what I was doing is I trying to looking at some of the other people, they wrote some code, but not for this, but for some like a bio samples, so they can control the column. Yeah, so Oxford has a version which trying to do the auto brightness contrast, but it won't work after a while. So you have to either write a script to adjust that. Mostly what happened is the contrast is too high. Yeah, that will cause a problem. Yeah, but I was able to kind of I can hop around the larger area and find a kind of a in the middle contrast brightness range, so that way when I zoom in I won't have that issue later on. Yeah, but yeah, there is some small script I might need a I haven't tried it. I ask people in the biology to help. So, but yeah.
Well, okay. Any other questions? Well, if not, I'd like to let's thank the speaker again, and thank you so much for sharing your work. It's super exciting. It seems quite relevant in terms of getting the most out of our data. And yeah, some of the tools that you're working on, it's going to be very, very, very useful. It looks like you're already working on some of the superconducting applications and analyzing the data. So we'll keep an eye on that. I certainly will.
Thank you for having me. Yeah, thank you.
All right, I'll stop the recording.